All right, Death Packet video number 2. This is questions 11 through 20, beginning with question 12. A scatter plot of a company's revenues versus time indicates a possible exponential relationship, a linear regression on y equals log revenue in 1000 against x equals 2005 gives y hat equals 0.075 plus 0.63 to the x. With R equal 0.68. Which of the following is a valid conclusion? So we basically have a log function here, and give me just a half a moment. I need to pause. Oh, so we have from years since 2005, and here they gave us a year 2009. So 2005 to 2009 is 4 years. So if I put 0.75 plus 0.63 times 4, I end up getting 0.75 plus 0.63 times 4 equals 3.27. All right. And if I do that correctly, 10 to the 3.27, because it was a log, if I undo the log, I get 18.62. All right. And so the predicted value is approximately 1,862. And you're like, well, wait a second, how did you know to do that? And basically, that by raising it to the 10 to the exponent is how we undo the log. And they already told us this was the log power. So the question came up was, why isn't revenue going up by 0.63? And that's a really good question because, hey, that's the definition of slope. There's 0.63 over 1, and this was revenue over years. Great question. And that's because they started off by taking the log of it. So basically, they took a nonlinear relationship that was exponential, and then they took the log of it. And when they took the log of it, then they got this relationship. So we had to undo the log to get back to the original relationship. All right, number 13. So which of the following are possible residual plots? First off, a residual plot must be centered on 0. This looks like a nice residual plot. For most part, because it's nice and random, everyone's happy, no pattern to it. I like that, but it's not centered on 0. Because it's not centered on 0, that gets rid of this one, so it gets rid of those. So now we're down till 2 and 3. All right, this one has a definite. You will not have a linear relationship on a log on a residual plot. This is some other graph. I'm not sure what it is. I don't, this could be a normal, I can't remember what it's called, but a normal plot. This could also be the actual scatter plot itself, but it is definitely not a residual plot because you should have points above and below the line without something like this happening. All right, so someone didn't do something here. And you kind of just have to know that one. This right here, you're like, well, wait a second. We have points above and below the line. It's like, yeah, that's because your underlying data happens to be is not linear. But this is exactly what you would get for a non-linear graph for residuals, and you try to put a residual plot to it. So this is probably like a parabola with underlying graph, and consequently that's why we got a residual plot. So the only one that's possible is 3. Okay, number 14. Suppose a study finds that the correlation coefficient relating job satisfaction to salary is +1. Which of the following is a proper conclusion? High salary causes job satisfaction. Correlation does not prove causation, so we can't say that. all right? High salary might be the result of me being satisfied. It may be the other way around. Low salary causes low job. Once again, I don't like the word cause because correlation does not prove causation. There's a 100% cause. Oh, there's that word again. There is a very strong association between salary and job satisfaction. Yes. Basically, they're saying, you know what? Every single one of them is on the line, so that's very strong. And there's no variation in it, and that is a very strong relation, correlation, or association. So D is my appropriate answer for number 14. Number 15, which of the following statements about correlation is true? When R equals 0, there is no relationship between the variables. No, when R equals 0, there's no linear relationship between. So this is a false statement because there's no linear. When R equals 0.2, 20% of the variables are closely related. That's not what that means. So R just tells you how close the data is, how close the observed is to the predicted line. So R is just a measure of how close it is to the observed is to the prediction. When R equals 1, there's a perfect cause and effect. Sorry, don't like cause. Cause is a problem. That's causing me issues. A correlation close to 1 means that a linear model will give the best fit to the data. Very, very tricky. When a correlation close to 1 means that it is a good predictor, but it doesn't mean it's the best predictor. You might need to try something out. You need to go do the residual plot to determine whether or not a linear model was appropriate. So just because we have a high correlation doesn't mean it's a good predictor. For instance, what if my data did this? Very, very close to the line, very, very close to the line, but I actually had a pattern to it. In which case, it's like, nope, it's not the best one. It's a good one, but not the best one. So in this case, as much as we hate that answer, all answers are false. All right, on number 16, consider the three graphs. Which has the greatest correlation coefficient? Well, first off, probably shouldn't have said the greatest, but which one is, it should have said probably which, the absolute value of which is the greatest, because these are all negatives, but which has the closest, which R is the strongest, might be a better measure. Well, when I look at these, it's like, you know what? Ignoring the scales, just looking at the data points, these data points are exactly the same. And I know they're the same because I made them here, then I copied it here, then I copied it there, and I changed the scale. Changing the scale does not change the correlation. So in this case, they have the same correlation coefficient. And you're like, well, I'm Mr. Spencer, I'm not so sure about this. Well, consider this. I draw a line for each one of them. When I draw each one of them, the data points are equal distance from the line. And correlation coefficients measures, it tells you how strong or how close they are to the line. And since they all have the same distance or all have the same relative distance, they all have the same correlation. All right, number 17, suppose the correlation between two variables is 0.28. What will be the new correlation be if 0.17 is added to all of the variables, every value of the y variables is doubled, and the two variables are interchanged? I love this equation. You should probably star it. Guess what? It didn't move the data points farther away from the line relative to anything else. And remember, correlation tells you how close the data points are, the observed is to the predicted. And since even though you swap things, even though you added, you didn't change how far any one data point is to the line relative to the rest. Consequently, your correlation is exactly the same. Please remember, swapping X and Y's don't change anything. And what if I had the equation Y equals 3X plus 5? Well, if I change it to Y equals 3X plus 7, and because I added 2 to all my, if I added 2 to all my Y values, if every point was on the line here and I added 2 to all my Y values, now my equation is Y equals 3X plus 7. If I doubled my X's and left them alone, left everything else alone, this would now be Y equals 6X plus 7, and everything would still be on the line. So these changes do not impact the R. They do not impact how close the data points are to the line. Number 19, consider the scatter plot of the midterm and final exam scores for a class of 20. Which of the following is incorrect? Well, first off, it starts off, both the correlation and the slope are negative. And it's like, yeah, I would say this is going downhill. And remember, correlation and slope will always have the same symbol. So since I have a negative trend, this is going to be a true statement, and we're looking for incorrect. We're looking for the false. The same number of students scored 100 on the midterm as did on the final. Well, oh, I got 2 here. I got 2 there. Same number. That's a true statement. The same percentage of students scored 100, scored below 50 on each exam. So I need to kind of look at this. And by the way, I'm not going to count all these up. So if I go this way and count over, or if I go this way and count down, turns out I'm going to have exactly the same. And all I did was sit there and go, you know what? That group scored below 50, count them up as a percentage. And then I do the same thing going this way and count these, and as a percentage, they're the same. So this is also true. Most of the students who scored below 50 on the midterm also scored below 50 on the final. So it's like, okay, this group scored below 50 on the midterm. I'll go ahead and make a dashed line. And I'm only not looking for these over here. I'm only looking for those. And then I go, all right, who scored below 50? And it's like, oh, only 3 of them. So that's not most, because I have this whole group that scored below 50. This entire group scored below 50 on the midterm. They scored above 50. So 3, this one right here is my false statement. My answer to number 19 is D. All right, so number 20, if the standard deviation of a set of observations is 0, what can you conclude? Well, let's talk about this. And I'm not sure how this made it into this data set, into this problem set, because it's probably not the best place for it, but the summation of x minus mu squared over n. For them to be, where n is a sample size, these are my individual values, and this is my mean. So this is a standard deviation formula. For this to be, for this to sum to 0, for all this to sum to 0, this numerator has to be 0, which means this value minus the mean has to be 0, and which means every single one of these values would have to equal the mean, which means every single one of them would have to be the same value. And if that would be the population, if it were the sample, it would be the same thing, but it'd be the summation of x minus x bar squared over n. And once again, the average of the sample would have to be equal to every single valuation, which means all the observations have to be exactly the same value.